Welcome to the Explainer. Today, we're diving straight into something absolutely mind-bending. We're talking about black holes. Probably the most deeply misunderstood objects in the entire universe. We are going to strip away all that sci-fi Hollywood stuff, look directly at the latest scientific models, and figure out what it actually takes to see the unseeable. So, let's get into it. Okay, let's dive into this by tackling a huge misconception. Because of pop culture, right, a lot of us grew up picturing black holes as these aggressive cosmic vacuum cleaners, just roaming through space, ruthlessly sucking up planets and stars like some sort of giant cosmic Roomba. It sounds super dramatic, but is it actually true? Are we all eventually doomed to be pulled into the abyss? To figure that out, here's our roadmap for today. First, the vacuum cleaner myth. Second, how black hole gravity actually works. Third, the accretion disk danger zone. Fourth, photographing the unseeable. And finally, shadows versus silhouettes. We're going to decode those famous Event Horizon Telescope images, and I promise, no crazy complex math involved. All right, Section 1, the vacuum cleaner myth, fact versus fiction. So the myth tells us a black hole is a cosmic vacuum, right? But the reality is actually a lot more mundane. It's really just standard mass with normal gravity. Think of it like this. It's a brilliant analogy. If someone magically replaced our sun right now with a black hole of the exact same mass, Earth wouldn't suddenly get violently sucked in. No way! We and all the other planets would just keep orbiting in the exact same path we're on right now. Sure, we'd freeze to death without the sun's light, but gravitationally, we'd be perfectly fine. Moving on to Section 2, how black hole gravity works, standard orbits. 4.7 billion. That is how many years our sun has maintained its current mass, keeping our whole solar system in a nice, stable orbit. And you know what? This principle scales right up to the galactic level. Our Milky Way galaxy actually has a supermassive black hole right at its core. Yet our sun, along with roughly 200 billion other stars, have been safely orbiting that galactic center for billions of years. A black hole doesn't reach out and grab things. Things just naturally orbit its mass. Section 3, the accretion disk danger zone, where matter actually falls. So if the rest of the galaxy is safe, you're probably wondering, where do things actually fall in? The answer is the accretion disk. While distant stars are totally fine, active supermassive black holes are surrounded by this incredibly hot, chaotic ring of material. That's where the safe orbits officially end. If matter, whether that's gas, dust, or just a seriously unlucky star, crosses into this specific disk, it's eventually going to hit the point of no return. And this brilliantly illustrates the chain reaction for that doomed matter. Inside the accretion disk, atoms are whipped up, moving incredibly fast. In that super crowded environment, violent atomic collisions happen everywhere, generating extreme heat. That heat forces the atoms to release massive amounts of energy as X-rays and radio waves. But here's the kicker. When they release that energy, they lose gravitational energy. And without it, they literally can't maintain their orbit anymore, so they fall inward. This inward fall is actually the only place where that whole sucking myth has any real basis in reality. Okay, Section 4, photographing the unseeable, catching light. To really wrap our heads around those famous telescope images, we have to look at how light itself behaves around a black hole. Specifically, something called the photon sphere. This is a region just outside the black hole where gravity is so insanely intense that photons, literal particles of light, are forced into orbit. They travel in these crazy spherical patterns oscillating around the black hole. Basically, to see a black hole, we have to observe how it manipulates this light. Take a look at the green envelopes right here. These show the exact regions where photons are just skimming and orbiting around an extremely fast-spinning black hole, also known as a Kerr black hole. The light gets trapped in these complex 3D geometric shells. They hang out there before eventually either escaping out to our telescopes or plunging inside forever. Which brings us to a really critical concept, the classical black hole shadow. According to general relativity, if you have a really bright, distant background, say a massive field of stars sitting way behind the black hole is going to cast a shadow against it. It is the maximum dark outline created by the black hole capturing the light from that distant background. See that large, lighter blue circle on the right? That's the classical shadow. And that multicolored line you see, that represents a single photon of light traveling all the way from a distant background star, winding around the black hole's photon sphere, and eventually escaping out to the observer. That escape is what forms a bright outline right around that large shadow. Now, if we track a luminous probe, like a compact star orbiting the black hole, the intense gravity basically acts like a cosmic funhouse mirror. It creates multiple light echoes, or lensed images, of that one single star. But here's the crucial part. Notice how all of those echoes sit strictly outside that dark central region? That central dark region is the classical black hole shadow we were just talking about. All right, final stretch. Section 5, Shadows versus Silhouettes, the EHT images. Now, what's really interesting about this is the dramatic contrast. On the left, we've got the massive classical shadow created by a distant background. But on the right, we have a notably smaller dark region, the event horizon silhouette. This smaller silhouette is exactly what you get when the black hole is highlighted, not by some distant background, but by the intensely bright, highly luminous matter of its very own inner accretion disk. And guys, here is the big twist the researchers uncovered. The famous Event Horizon Telescope image of the M87 black hole, it does not show the classical shadow. Why? Because the accretion disk swirling around it is so insanely bright that it completely washes out the distant, dimmer background stars. Instead, what we're actually looking at is the lensed, dark image of the southern hemisphere of the black hole's event horizon itself, highlighted perfectly by that glowing accreting matter. And the specific size of that dark spot? It agrees completely with models of a thin accretion disk around a highly spinning black hole. To really cement this, listen to this direct quote from the researchers who analyzed these geometries. Quote, "The first image of the supermassive black hole, M87 star, shows the lensed dark image of the southern hemisphere of the black hole event horizon globe, while the classical black hole shadow is invisible at all." End quote. I mean, that fundamentally shifts our perspective, doesn't it? We are seeing the dark silhouette of the event horizon globe itself, framed by the very accretion disk we mapped out earlier. Absolutely mind-blowing. So, we've totally busted the vacuum cleaner myth, we've mapped out the danger zone of the accretion disk, and we discovered that our famous first pictures of black holes are actually silhouettes of the event horizon, not classical shadows. As we wrap up this explainer, I really want to leave you with a provocative thought. If we can decipher all of this from our current imagery, what will future cosmic interferometers with nanosecond resolution reveal next? Honestly, we are just at the very beginning of actually seeing the mechanics of the universe. Thanks so much for joining me on the Explainer today. Keep asking questions, keep looking up, and I'll catch you in the next one.